Hello, everybody. This is Elizabeth from your logic class, Phil 2001. And this is my third time recording this because in the previous two times I made some errors that, while trivial, would have taken a long time to go back and fix and explain. They just wasted a lot of time because I wasted a lot of time, basically, dealing with something that wasn't correct. So, forgive me, my voice is a little hoarse. I decided to make some video tutoring examples because lately I've been using Khan Academy and I think it's fabulous. And I know that a lot of people in this class have been having had trouble with Unit 1. And I know that Unit 3 builds on Unit 1, and I really want everyone to do well on the final exam. So I thought I'd make some tutoring videos to help everyone out. So I'm doing example 3.8 from Greg Restall's book. It's on page 52. I chose it mostly arbitrarily, but partially just because it looks kind of weird and overly complicated. But if we look at it and we think about it a little more deeply, then we'll see that it's actually not that complex, and then we'll use a truth table to evaluate it. So it says, I will get a pet or buy a cuckoo clock. If I get a pet, I will get a monkey. I will buy a cuckoo clock only if I meet a persuasive clock salesman. Therefore, I won't both not get monkey and not meet a persuasive clock salesman. Well, okay, so not only is this person crazy, this argument sounds kind of crazy. But we know that if we look at some of these premises, he says if he gets a pet, he'll get a monkey. And if you look at it, the conclusion does not rely on him getting a pet; it just relies on him getting a monkey. So if he gets a pet, then he will get a monkey. So if that implies if this is P and that is Q, and P implies Q, then that means that whenever he gets a pet, then it's the case he got a monkey. It will always be, if this is true, then this is true. So for the purposes of this argument, they're actually kind of equivalent. And if we look at the third premise, that's actually kind of the same thing. For the purposes of this argument in particular, it says that I will buy a cuckoo clock only if I meet a persuasive clock salesman, and that means that cuckoo clock implies persuasive clock salesman. And that's because if you say that it's true only if, well, what do we know about the truth table for the horseshoe? We know that the antecedent must be true if the consequent is true. So, excuse me. The consequent must be true if the antecedent is true. That's the first thing I said there wasn't true. Ignore it. The consequent must be true if the antecedent is true. So, if we think about it, this first one, if we call I will get a pet P and buy a cuckoo clock Q, then that's sort of a P V Q, P wedge Q. And the last one is if we say that pet and monkey are equivalent, and if we say that cuckoo clock and clock salesman are equivalent, then that is the same thing as saying it's not the case that not P and not Q. And you'll probably remember that these two are actually exactly the same things. There are different ways of saying one thing. This is just how you express the wedge connection in terms of tilde and ampersand. So that makes sense. This argument we know is valid, and the kind of neat thing about that for me is that it shows that it's an example of how arguments are just kind of like meta propositions. They're premises and conclusions, but if you wanted to, you could just rewrite them with lots of parentheses and ampersands, and a horseshoe is the main connective. And then you would have a proposition, and this particular proposition would be tautological. And tautology for a proposition is the same as validity for an argument, because it means that it's true in every possible case of the truth of the propositions, the atoms, and that's how we know it's valid. So just to make sure that our intuition here is correct, let's actually go through and we'll use all of these different propositions and make sure that it's correct using a truth table. So we'll get a pet. I will get a pet is P. I will get a monkey is Q. I will meet a persuasive clock salesman is R. And oh, sorry. So I will get a pet is P. I will buy a cuckoo clock is Q. Monkey is R. And persuasive clock salesman is S. So we'll put in our propositions. We'll do P, Q, R, S. And then we'll just fill in the combinations of values for this. And this confuses people because they're like, oh, well, it says it's right that P or Q, so why do we have to consider the rows where P or Q isn't true? And it's because we're assembling evidence for this proposition, and we're trying to find, for this argument, we're trying to find a counterexample, because that is the only thing that could prove that it's not true. And since we have only 4 premises, 4 atoms, 4 things that we have to test, we can, in the case that each one is true, is the argument as a whole true? And if it's not, then it will be invalid. So we have to look at the cases where the very atoms are false, even if that would make if that would seem to contradict what the argument says, because we're testing for validity, not soundness. So it's to be the case that if these atoms were false, then the argument would still hold. And that would happen if all the atoms were false and the conclusion was false too. So that's how that works. So we fill in these ones and zeros. So we should have 8 ones and 8 zeros for each atom. So let's get to work actually translating these premises. So it says, I don't have enough columns here. It says, I will get a pet or buy a cuckoo clock. And as we already established, that's just the same thing as P, wedge, Q. If I get a pet, I will monkey. That means it's an if-then statement. If pet, then monkey. So, it is, P implies, well, I'm not going to use that color, implies R, and I will buy a cuckoo clock only if I meet a persuasive clock salesman. Again, that's an if-then statement, although phrased a little weirdly. So it's Q implies S. And if you think about it, it's sort of like, you know, only, I will only have bought a clock if I met a persuasive clock salesman. Therefore, the buying the clock implies that I met the salesman. I was actually wrong about not having the correct number of columns, so I'll just delete that one and rewrite this quickly. And then let's write the whole conclusion, which is not the case that both not P and not S. So now our first task is just to push all these values across. And this is a pretty mechanical task. So we just copy out all the same values. That we had here. I feel like if I were saying all these ones and zeros to a computer, I might accidentally be saying something very offensive in binary. Oh. It should be 4 and 4, not 2 and 2. My mistake. Because we're just copying these right now, we're not doing anything special with them. And I'm sorry if copying them takes so long. That is one of the reasons why truth tables suck, and we will leave them later. Leave them high and dry. So this one is 2 and 2. 2 zeros for 2 ones. And they all have the same number I mentioned as... Oops, did something wrong here. Yes. They all have the same number of ones and zeros. They're just arranged so that we get all the possible combinations of their truth and falsehood. Wrong color. 0. Okay, now that we've got all these values pushed across and everything looks all colorful and crazy, we're going to evaluate the main connection of each premise using the truth tables for those connectives. And we already mentioned that for the wedge, it's only false when the atoms are both false, and in every other case it's true. So false for those 4 rows, and then we'll see that the rest all have at least one of them true. So we'll just throw in a bunch of ones here, turtles all the way down. And then for the horseshoe, these 2 are going to have the same rules apply to them. They're always true if the antecedent is true, and they're always true if the consequent is false. Or, sorry, they're always true. They're always true if the antecedent is false, and they're always true if the consequent is true. Pardon me. They're always true if the antecedent is false, and they're always true if the consequent is true. Because they're only false in the case where the antecedent is true and the consequent is false. So we can immediately say, well, the antecedent is false in all these cases, so I know it's a bunch of ones. It has to be true. And in this case, we're like, well, the consequent is false, the antecedent is true, 0, 0, 1, 1, 0, 0, 1. And we can just do the same thing in this row. So the antecedent is false, so for all of these, it's going to be true. I'll just mark these 2 in here too. 0, 1, 0, 0, 1, 0, 1. Now we can evaluate these knots, and the knot values, of course, are just going to be the opposite of whatever value the atom is. So in this case will be 1, 0, 1, wrong color. And I just told the computer that his mother was fat. So now we can evaluate this ampersand, which is kind of the main connective of this mini proposition here. And ampersand, we all know, is only true when both of the atoms are true. And both of the atoms in this case are not cases, so they're not P and not S. And so we see in the first row it's true. And for the first 8 rows, it just has whatever value S has, because P is true for all of these rows. So, I mean, it has whatever value not S has, because not P is true for all of these rows. So we can just say 0, 1, 0, 0, 0. And then for all of these rows, we know it's going to be false, because not P is not the case in these rows. So we can just copy down a bunch of zeros here. And finally we can get to the main connective of the conclusion, which is not, which means only that we just have to copy out the opposite of the values, again, of the ampersand. So all of these false ones quickly, that's going to be true. And then that's going to be false, true, false, true, false, true, false. So finally, we have the means to evaluate our argument in terms of our main connectives. And we look at the different rows of the different columns of the truth values of the connectives, and we see if there's any rows where all the premises are true, but the conclusion, the main connective of the conclusion, is false. And since we know that in the truth table for the horseshoe, it's always true, the whole thing is true if the consequent is true, we can immediately get rid of all these rows down here that are the bottom 9 rows, because the consequent is true in all of those rows. So don't do this on your test, but I'm just going to get rid of all these to show that, hey, it doesn't matter what's up with them, because they are all inherently true instances of this proposition. And then we're left with something slightly simpler, and we look for a row where all the premises are true to see whether the conclusion is or false in that case. And we see right off the bat that the premises are not all true in this case, because the wedge here is false in these 4 cases. So we're going to get rid of these rows too, and now we're left with only 3 rows, and we say, okay, so are all the connectives true here, or all the premises true here? And we'll find that there's only 1 row where all the premises are true. And in that row, the conclusion is, oops, I'm trying to make my grand finale. The conclusion is true. So our intuition on that was correct. This argument is valid. If we wrote it all out as a kind of big-ass proposition, we would see that it's a tautology. So thank you very much for listening to this final recording of my video. Although I did make some slips of the tongue, I corrected them and did not make any major errors in evaluating the argument. So I hope you'll join me next time. I'll be doing exercise 3.10 on page 52. Enjoy!